Hi, my name's Liam Taylor-West. I'm a composer currently working with mathematicians at the University of Bristol. In the last video we talked about periodicity and created periodic and aperiodic sequences by repeating an event over and over and writing down the outcome. I now want to introduce you to two new mathematical ideas that we'll need to understand when thinking about how those sequences from last time were made. Both these ideas are to do with the word predictability. If an event is predictable, you can tell what the outcome is going to be before it happens. If an event is unpredictable, then you can't tell what the outcome is going to be until it happens. I'm going to talk about predictability a lot when introducing these two new ideas. The first of these ideas is the concept of randomness. If an event is random, then there's no way of knowing what the outcome is going to be before it happens. Flipping a coin is a random event because you can't tell whether it's going to land heads or tails next. That's why a coin toss is used at the start of lots of sports matches to work out which team is going to play first. Rolling dice is a random event, which is why dice are used in a lot of board games. It adds a level of unpredictability to the game. So, what do we call an event or process that has no randomness in it at all? Mathematicians call it a deterministic system. A system is just a word for a collection of things that work together to achieve a common goal. A deterministic system is one that includes no randomness in that process, meaning that if you know the current state of the system and you know the rules of the system, then you can work out what will happen next. That sounds complicated, but deterministic systems can be really simple. Do you remember me switching the light on and off in the last video? That was an example of a deterministic system. The rules of that system are: if the light is off when you press the button, the light will turn on. If the light is on when you press the button, the light will turn off. If you know those two rules, and you know that the light is currently off, then you can predict whether the light will be on or off after any number of button presses. After one press, the light will be on. After two presses, the light will be off. After 10 presses, the light will be off. After 3,605 presses, the light will be on, and so on. Looking back at the sequences we made in the last video, you might have noticed that the periodic sequences were created using deterministic systems, and the aperiodic sequences were created using random ones. We've talked about pressing the light switch and flipping the coin, but what about the others? If we think about the days of the week, you can see that that is an example of a deterministic system, because if today is Monday, then you can tell that tomorrow will be Tuesday and the day after will be Wednesday, and so on. There are rules that tell you which day will come next. And the colour of cars on the street could be seen as a random event, because you have no control over what car will drive past you next. So let's set up a deterministic system. I'd like you to imagine that you're in a car driving slowly down a very straight road. Think of Olivia Rodrigo in her driver's license video. You can imagine that as long as the road doesn't turn and as long as she doesn't stop or turn around, that anything that lies up ahead of her she will eventually reach. If there is a bridge going over the road about a mile ahead, we can confidently predict that she will eventually drive under that bridge. Now, instead of imagining that we're driving down a straight road, let's imagine that we're flying in a straight line and looking down at the ground beneath us. If you've ever played the game Fortnite, you'll know that each game begins with a map of the island and a path drawn across it, which is the path that the battle bus is going to take. In the same way that we can predict that Olivia Rodrigo will drive under that bridge eventually, we can predict that the battle bus will fly over Loot Lake in Pleasant Park in this example, and that's because it's travelling in a straight line. This map even has squares drawn onto it, if you can see that, and that way we can predict which squares the bus is going to pass through. Let's stick with these squares for the time being, and imagine that instead of flying over the Fortnite map, we're flying over a city that is laid out very regularly in squares. Los Angeles in America is very square in its design, as you can see from this map of part of the city. Streets in Los Angeles, or LA as people call it, are often given names like Avenue or Boulevard. So let's say that every time we fly over a street that goes vertically down from the top to the bottom of the map, we write down an A for avenue. And every time we cross over a street that goes horizontally across the map, from left to right of the map, we write down B for boulevard. You can see that our path would create a sequence of A's and B's depending on which streets we flew over. So, let's make a sequence by following this path over LA. Okay, so now I'd like you to create your own sequences. Instead of flying over Los Angeles, let's simplify it and let's just use a grid of squares. I'd like to choose a starting point on your grid at a crossroads where the corner of 4 squares meet. Then count up a number of squares. In this example we're going to count up 2 squares, and then count along some squares to your right. In this example we're going to count 3 squares. This should get you to another crossroads. I'd like you to draw a straight line between these 2 crossroads and continue that line off to the edge of your paper. Now, go back to your starting point, which is that corner, and travel along your line. Every time you cross a street that goes vertically down from the top to the bottom of the page, I'd like you to write down an A for avenue, and every time you cross a street that goes horizontally across the page, I'd like you to write down a B for boulevard, and see what the sequence of A's and B's comes out as. When you hit a crossroads where the vertical lines and the horizontal lines meet, I'd like you to write AB. Make 3 sequences like this, and then let's come back and discuss them. To make my sequences, I've created another max patch. We're going to count 3 squares up and 2 squares along and begin our journey along this path. As the sequence grows, we can look at it and try and work out whether it is periodic or aperiodic. As we can see, the full sequence can be broken down into a smaller chunk of BABAB, meaning that this is a periodic sequence, and the period of this sequence is BABAB. If you look at your sequences, you should hopefully notice that they are periodic, just like mine was, and that there's a smaller chunk of your sequence, the period, that repeats as you move along your path. Have you worked out where on your path your sequence starts repeating? If you count out the period of your sequence along your path, you'll notice that it ends every time you hit a crossroads. This makes sense because your journey started in a corner, so every time it hits a crossroads, it's a bit like it's repeating and starting again. The sequence that our path creates depends on the number of steps we took up and the number of steps we took along. So, in the first example, where we went up 3 steps and along 2 steps, then our sequence is comparing the numbers 3 and 2. We could say that it was 3 against 2. So, for the next example I asked you to do, we went up 4 steps and along 3 steps. This sequence will be comparing the numbers 4 and 3. What sequence does this create? We can see here that the period of this sequence is longer than the one before. That's because we've had to travel further along our path to reach the next corner point. What if we go even further? Let's go up 6 squares and along 4 squares. This sequence looks familiar, right? The period of this sequence is the same as the one we got when we took 3 steps up and 2 steps along. If we look back at our grid of squares and count up 6 squares and along 4 squares, we can see that our path goes through a corner point, a crossroads earlier on in the journey. To reach this crossroads, you could go 3 steps up and 2 steps along. That's why the sequences created from these 2 paths were the same. So, how do we make music out of this? What if every time you crossed a line, instead of writing down A or B, you made a sound or played a note? Let's replace A with a kick drum and B with the snare drum and see what some of these sequences sound like. In music, we call these patterns polyrhythms. Poly comes from the ancient Greek word meaning many, and as you can probably hear, it sounds like there are two things going on at once. We know that the period repeats every time we hit a crossroads, and in musical terms, a crossroads is when the snare drum and kick drum sound at exactly the same time. So, within each period, you can see that there are 4 snare drum hits and 3 kick drum hits, which is the same as the number of steps we took up and along. This pattern is comparing the numbers 4 and 3, and we call it the 4 against 3 polyrhythm. To find out more about these polyrhythms, I spoke to Georgie Ward, a pianist and synth performer seen playing here with Zara Larsson in one of her recent videos. What Georgie's doing here is creating a slowed down version of the 4 against 3 polyrhythm by tracing the outlines of a 4-sided shape and a 3-sided shape in the air in front of her. This makes the relationship of 4 against 3 really clear. Rather than drawing them in the air, I'd like you to draw your shapes on a piece of paper. We're going to play a drum beat in the background, and keeping in time with the beat, we're going to tap round the corners of our shapes. We're going to choose one corner to start from, and every time we hit that corner, we're going to make some sort of noise. You'll see that tapping around the corners of the rectangle and the triangle gives you a slowed down version of the 4 against 3 polyrhythm. The 4 against 3 polyrhythm appears in music all the time. Listen to this excerpt from the song Symphony by Clean Bandit and Zara Larsson. Pay particular attention to the synth and the bass against the drums. It might not be immediately obvious, but this is the 4 against 3 polyrhythm. The synth and bass play 4 notes in the same amount of time as the drums play 3. It's harder to see when being played at this speed, but Georgie's left hand plays 3 notes in the same amount of time as her right hand plays 4. When you compare this to the path we took over the grid of squares, Georgie's left hand plays a bass note every time we cross a vertical line, and her right hand plays a chord every time we cross a horizontal line. So, what about creating periodic sequences from random events and aperiodic sequences from deterministic systems? It is certainly possible to create a periodic sequence from flipping a coin if it were to land heads, tails, heads, tails, heads, tails, for example, but it's quite unlikely for that to happen. A mathematician could tell you exactly how unlikely that is to happen. But what about a deterministic system creating an aperiodic sequence? This would be a sequence that never repeats, but one where you could predict what would come next in the sequence as it got longer and longer. All of the sequences we created today we made by following a path over a grid of squares, where we started in one crossroads and passed through another one. But what if your path never hit another crossroads? What sort of sequence would we get then? We'll find out what happens in the next video. Thanks for joining me, see you then.